Hi, everyone. I am very excited to introduce our speaker today, Dr. Samantha Kleinberg. I've known Samantha for a very long time. When did we meet?
Not that long. You make it sound like.
Maybe 5 years ago?
Yeah, that's good.
Yeah, 5 or 6 years ago. And we were not at the same institution or anything like that. We met at a conference, and I instantly knew I liked her because she made a very bad joke of the dad variety kind, which is my favorite kind of joke. But Samantha has done a lot of work in causal inference, and importantly in non-theoretical causal inference, also applying principles of causal inference to real data, which is a field that I believe very strongly in and that I think is underrepresented often in the machine learning space and in the machine learning for health space. Samantha also has tenure, which is life goal for me, but she is going to be on sabbatical next year at UCL doing some work in experimental psych. So she's going to talk to us today about her recent work where she's looking at these methods from the lens of causality. Everybody, please give a warm round of applause for Samantha.
Thanks so much to Marcy for inviting me. I probably won't tell dad jokes, but we'll see. Okay, so I know everyone's color-coded with computer science or health. I'm on the computer science side, and then by the end of the talk, you'll see why I'm doing a sabbatical in experimental psychology and why I think it's necessary for my work. So this is the sort of problem that I think about. This is a stroke patient in the neuro ICU at Columbia. When a doctor walks in, they see a huge number of monitors. It's really hard to figure out what's going on, what they should do about it. It's also a sort of terrible HCI problem. All these things are disconnected. Nothing is talking to each other. This happens to be an advanced ICU that actually stores the data. A lot of ICUs don't. At Columbia, I think this is the only ICU that actually does. The other ones, you're lucky if you see something that's important when you're walking by or someone writes it down. And after that, it's just gone forever. And so it's sort of astonishing as a computer scientist, right, that there's this huge data source that's really underutilized that could potentially be used to help clinicians, how to treat these patients. So one of the challenges has been the computer science solution has been alarms. We figure out what bad things are happening, we send an alarm, and then tell doctors bad things are happening. The challenge, of course, is these are extremely ill patients in the neuro ICU. Lots of bad things are happening. Not all of them can be treated. Many of them can't be treated, right? And so doctors develop alert fatigue, and they start ignoring alarms because alarms are going off all day long. There have been other works showing doctors actually can't tell the difference between the sound of all different alarms. And then as a result of all of that, important alarms get ignored. And so there have been a number of cases where patients died because there was an alarm that got ignored that actually was meaningful. But if you're a doctor who's super busy and in the ICU all day, you don't have time to sift through all these different alarms and figure out which ones are usable and which ones aren't. So I've been collaborating with clinicians for a long time, and really what doctors want to know is not just what's happening, but why is this happening and what can they do about it, right? And figuring out what are the actionable things. So the first part of the talk will be how do we actually get knowledge from. Oh, sorry.
Sorry, we all want to hear.
If you can't hear me, just shout or say something. I don't know if that's any better. Yeah? Oh, good. Thumbs up. I appreciate feedback. And raise your hand if you have confusion or questions about anything during the talk. So the first part is how do you actually extract knowledge from all this ICU data and medical data? And then the second part, I'll talk about how do we go from knowledge to actually actions, which is what we want to do. So first part, data to knowledge. The first thing I want to convince you of is if you want to get knowledge from data, you really want causal knowledge if you want to do anything with this. And so if you're a computer science person or on the machine learning side, a lot of people have argued maybe we don't need causality. Causality is really hard. We can extract patterns from data, especially as deep learning has become more popular. We can make really accurate predictions, and so maybe let's give up on all the causality stuff and just settle for pattern mining. And this is one of the quotes that I sort of like to pick on about this. But I've tried to argue any sort of action requires causal knowledge. And I have poor time management, write a lot of books about this. So first example is prediction is one of the things that people try to convince you don't need causality for, right? If you just want to know what's going to happen, maybe pattern mining is enough. Probably in this room, a lot of you are familiar with Google Flu in the US. And so Google Flu at first was a success story, and now it's mostly popular when I ask people about it in a negative context as a major failure, right? And so this was a case where Google was able to accurately find cases of the flu earlier than the CDC. It seemed quite accurate at first, And they were doing this based on search keywords. The problem with that is there's no real reason for you to search for the flu that's linked to you having the flu. You might hear about flu cases on the news, your friends have the flu. There's a very tenuous connection between what you're searching for and whether you specifically have a case of the flu. And so what happened ultimately was Google Flu was massively overpredicting cases of the flu. And then as a result, most of the articles people are familiar with are the failure of Google Flu. Right, so if you want a robust prediction, what you need are causes, right, that are actually relating what's happening to why it's happening. The second thing we want to do with causal relationships or with information we get is explain. Often we have time series data or other types of data that have similar patterns. Why are these things related? This is one of my favorite websites that finds spurious correlations. And you can find lots of fun time series on the web. A lot of things end up being related to cheese. There's like computer science doctorates in cheese. I don't know. I think there's a lot of non-stationary fun cheese time series. But I could show you other time series, right? I could say, maybe it's screen time or use of smartphones and autism. And then people would start to come up with stories of why these things are related. But there's no reason for the relation here other than these are non-stationary time series, right? So even if you want to understand this, you need causal relationships. Another type of explanation is why did a specific event happen? So why did this particular car crash happen? Why is this particular patient's brain swelling right now? And for that, you need not only causal relationships, you need to know a cause of a specific instantiation of an event. And this is something my group has worked on automating. It's a really hard thing for humans to do. We tend to focus on things that happened immediately before the event. So you go to the doctor, you get a flu shot, you end up with the flu right after, and then people think, the flu shot caused it, right? Because that happened right before. Even though it's crazy, the flu shot can't cause it. Whereas here, in this example, this is a patient with diabetes. They go for a run, they have a snack after the run, the glucose goes up. Later on, they have lunch and give themselves insulin. And it's only the combination of these two events that causes hypoglycemia. But it would be very, very difficult for you as an individual with diabetes to look at this time series and say, yes, it was the first event or the second event or the combination of events. It's really basically impossible to look at this without any other automated methods. And so for explaining why things happen, causality is quite important. Last thing we want to do is control the world, control patients, prevent bad outcomes, make good things happen. And for this, we need not only causes, but we need to know why the causes are effective. So this was an example where Tennessee did randomized trials with class sizes. They found smaller class sizes led to better standardized test scores. Regardless of whether standardized test scores are a good thing to optimize for, that was what they found, right? And then so California looked at this and said, okay, smaller class sizes, that's the thing to do. We'll give people incentives to make their class sizes smaller. And what happens when you implement this in a much larger state? Well, you need more classrooms because you have more classes, right? You need more teachers. There's not an unlimited supply of really good teachers. And so they ended up with teachers that were less qualified. They took rooms away from other programs like computer science or physical education. And then it failed there, right? Because you don't have the conditions necessary for the cause to be effective. And so you need not only to know, right, that the smaller class sizes are the cause, but what are the other things that make the cause effective, right? And so, just a correlation here would be completely useless for making an effective intervention. Okay, so assuming you're convinced that causes are a good thing to have, why on earth would we want to do this from observational data, right? If we really want causal relationships, why not do randomized trials or at least some sort of experiment, right? First is, in a lot of cases, it's not feasible to do a randomized trial. One of the examples I'll talk about here is congestive heart failure. I also do work on type 2 diabetes. If we want to understand risks for type 2 diabetes, we'd have to follow people for an extremely long time to find out when they get type 2 diabetes, right? And so it's much more useful if we can go backwards with data that we already have and understand what are the risk factors versus waiting 20, 30 years to figure out, okay, how should we treat patients today? And then by then things have changed. And then in other cases, it's just unethical to do experiments. What's been exciting as a computer scientist is the large amount of data. Data has problems, but there are a lot of interesting data sources. And so electronic health record data, intensive care unit data streams like from the neuro ICU, and then also patient-generated data. And so especially for chronic diseases, there are lots of individuals with type 1 diabetes who use continuous glucose monitors, insulin pumps, who track their activities, people with other diseases who also track a lot of symptoms and signs, as well as activity and other features. And we could potentially learn from that, right, and learn what's happening in between hospital visits. And so I'll talk about a few problems today. These are the sorts of things we work on with causal inference. Can we identify risk factors for heart failure from electronic health record data? Can we find why specific people have hypoglycemia or hyperglycemia? Again, using outpatient data that's very noisy and messy. Can we find causes of secondary brain injury? So what's happening during recovery from stroke? And we want to do this only from observation. So I'll talk about some problems from doing that and some successes. So when I say causal inference, this is what I have in mind. For the non-machine learning people, this is as much math as there will be, and then you don't need to know everything that's on the slide. And so the thing that I want you to know is I don't think of causes as one variable causing another, and that's the end of the story. I think in many cases, especially in health, timing is an enormous part of the causal relationship. We want to know, when are people going to get stroke? When is medication going to take effect, right? When are you going to have hypoglycemia after you exercise? And that's something we want to learn also from the data, right? And causality can be complex. It's not just one variable causes another. It might be a variable being true for a duration of time, right? So exercising for 20 minutes has a different effect on your glucose versus exercising for an hour or an hour and a half. And want to capture that. And so we can represent complex things like that. And so all the top is saying is vigorous exercise causes hyperglycemia in 15 to 40 minutes with some probability. And so it's just showing we can find this. Yeah, I won't say any more about that. Finding variables is hard, but that's a separate problem we won't address here. And then how do we actually find which things are causes? The idea is sort of trying to do experiments in the observational data. And the idea is if we keep everything constant, so like doing a randomized trial, if everything's the same and we turn the cause on and off, then there should be a difference in how likely the effect is or what value the effect has, right? And so if I keep everything fixed with your diet and exercise and just change your stress levels somehow, then if that's causing changes in your blood glucose, I'll see a difference in blood glucose even if everything else is the same when I change your stress level. And so that's what the second part is doing. Okay, that's all you need to know about the mathematical stuff. And so then I want to talk about 3 challenges and sort of how we solved them. So one is, especially in health data, it's really, really difficult to interpret your results, especially without clinical guidance, understanding what the variable is and what you're actually measuring. So even just what is a diagnosis? What does it mean for a patient to have heart failure? It actually turns out this is not quite obvious. The second thing we had to deal with was uncertainty in the data. This was especially true in the diabetes data. There's very high error rates with glucose monitors. And so how do we actually know that the patients are having hypo or hyperglycemia? And so if we want to do causal inference, it's actually quite a large challenge if we don't know if the event we're interested in is true or false. And finally, there's a huge missing data problem in all these data sets. And again, for causal inference, things are measured for a reason, especially in the ICU. We have no ability to change what the doctors choose to measure. This depends on the patient's health status, the patient's insurance status, all these things. And if we just ignore the missing data or don't account for the missingness process, then we're going to have confounding in the causal inference. And there are lots of other challenges I won't talk about here. It's just that, yeah. There's an endless array of problems to work on in causal inference and observational data. I get tempted to talk about all of the problems. Okay, so the first application is with electronic health record data. So showing we can learn something from this data, but it can be hard to interpret. So the first challenge was, what does it actually mean for a patient to have heart failure? If we want to find causes of some outcome, like a disease or diagnosis, we have to identify which patients have heart failure. If we want to identify when the risk factors happen, we also have to figure out when the patients have heart failure. And that's really hard because we're not observing the heart failure itself, right? We're observing diagnosis of heart failure, which happens at some time after the heart failure actually happens. And this is a chronic progressive disease. And so there's some underlying damage to the heart that's happening over time. And then it becomes clinically apparent and is diagnosed, right? But we're not seeing that process. We're seeing the medical process, and then we assign a time to it and say who's a case or a control, which leads to some problems, right, in identifying the start time of these events. But even so this was data we got from Geisinger Health System. This was electronic health record data from about 30,000 patients over, I think, around 7 years. And we do find some risk factors for heart failure with interesting timing. So hypothyroidism, being diagnosed with diabetes, being overweight. And then the interpretation becomes difficult, right? You see, being on an antihypertensive medication seems to cause heart failure. It actually turns out the blood pressure is an extremely noisy measurement, and your blood pressure in the EHR didn't really tell us if you have hypertension. But being on a medication gives us a much better indicator for that. And so again, like if you're just looking at the data and you throw it into your black box and you don't have clinical guidance or insight, it's really hard to understand what's happening. And the same thing with the urinary symptoms. It turns out it was mostly due to frequent nighttime urination, which is a symptom of heart failure. And so we're finding actually that's happening 8 to 11 months before the diagnosis. It's causing the event of the diagnosis, not causing the heart failure itself, right? And so remembering, we're only finding causes of diagnosis. We're not actually finding causes of heart failure. And so again, interpretation is really, really difficult. But we were sort of excited. We actually found some causes. The timings made sense. These related to things that were already known. But for chronic diseases, electronic health record data isn't necessarily the right data to use. If you have diabetes, maybe you see your doctor a couple times a year, but you're the one deciding every time you have a meal how much insulin you should give yourself, right? And how you should adjust for your exercise, how you should adjust for your stress level, all these other factors. So there, we thought it's more interesting or important to use free living data. And so data from patients going about their daily lives. On the other hand, once you move to uncontrolled environments, you have many more challenges with uncertainty. The sensors are consumer grade. People do all sorts of unexpected and unpredictable things in studies that you couldn't envision they would do. They break sensors. All sorts of things happen, right? And so uncertainty was a giant challenge. So I won't talk about the methodology, but basically the thing we did was incorporate uncertainty measurement into the causal inference process. And so data points that we trust more, we learn from them more strongly, versus data points that maybe you're on the edge between, let's say, hypoglycemia and normal glucose, then those we're sort of more skeptical of, and they don't contribute as strongly to the findings. And so modeling that when we're figuring out causes of hypo or hyperglycemia. And then this was data with only 17 patients over 3 days. It's a very small data set, right? 72 hours of data for 3 people. But once we were able to model the uncertainty, we were able to learn from the data. And so we actually did find causes of hyperglycemia. These were known, so intense exercise makes glucose go up, moderate exercise tends to make it go down. But it's something that had been found before in very controlled environments in exercise physiology labs. And so it was really exciting that we're able to do this with extremely messy data just from daily life, right? By modeling uncertainty better. So going back to main application, these were exciting, still very few data points, right? 3 days for 17 people. The other one, it's a few years of data for each person, but still not that much data on each individual if you're looking at hospital data. In the neuro ICU, you have a huge amount of data on each individual. This data set for 98 patients was basically the same size on disk as data for 30,000 patients with EHR data, just to give a sense of how intensely monitored they are, right? Which brings good and bad things, right? So you have about 100,000 measurements for each person. A lot of the monitors are every 5 seconds. So what was exciting was the idea that maybe we could model people individually in the ICU. And we wanted to understand many questions. The first and most fundamental one was, what's happening during stroke recovery? And I'll talk about other challenges and successes. So in this data, we had a number of patients with a form of hemorrhagic stroke. We had EEG on the surface of the brain, EEG within the brain, brain metabolism, all sorts of physiologic measurements. That was very exciting. What was not as exciting was huge amounts of the data were missing. And so, devices have malfunctions. Patients are sick, they have surgeries, there are procedures, things are disconnected to perform these procedures. Things are started at different times, right? I mentioned we have no ability to control the medical process. Things are measured because they're thought to be clinically relevant or useful. And so not everything is started on day one. Even if a patient does have everything measured later on, things are started at different times. And that progression also has meaning, right? It tells you about the patient's status. Other things are measured at different recording frequencies. Some variables are every hour and written down by a human, or sort of every hour, kind of. Other things are every 5 seconds. So just to give a sense of how bad the problem is, this is showing what percentage of the theoretical maximum amount of data we could have that we actually do have. And so I've shown this to computer scientists who said, why wouldn't you ever do this? Why wouldn't you just do theory instead of working with this data? Which is sort of a depressing take on it. I tell prospective students there are lots of problems to solve. That's the more positive spin. But clearly there's a huge problem with missing data, right? And if we ignore that, then we have a huge confounding problem for causal inference. If we just say, the data's either there or not, we'll put 0 or nil value if we don't have missing data. The other problem is for a lot of imputation methods, it assumes that you have at least some data at that time point. And so if you're going to find nearest neighbors or something like that, it assumes you at least have one measurement so you can find nearby time points and measurements. On the other hand, we have a lot of instances where you have absolutely no data whatsoever for that time point, which happens if things are disconnected, right, to perform a procedure, then all variables are missing. In other cases, a number of variables are all measured by the same device, so if one is missing, they're all missing. Right, so you have all these challenges. So we introduced new methods for imputation of missing data that allows for multiple types of missingness processes. And basically the idea behind it is a lot of these variables are correlated but with a lag. And so actually the relevant data to use if you're imputing new values for the missing values is historical data. So for example, here you have X, Y, and Z. And if you want to impute a missing value for X, actually you want to use older data from Y and Z, right? Because they're related with these time lags. So that's the basic idea. Is we had lagged k-nearest neighbors, Fourier transform for the part of the missingness that depends on the variable itself, and this was our approach. But the real goal was causal inference and time series, and then we solved lots of other problems along the way to get to this. It was 5 years of other problems before we got to the causal inference in this data set. And so it was very exciting. We finally had causal relationships we believed. At the end, this is showing only brain-related variables and causal model for the first around 4 days after stroke. And so the numbers also are showing the number of patients that had that causal relationship, and the percentage is how many people had those variables measured. And so that's because things are measured for different people. We might have a variable measured in 7 people, and so if we find it in 5 out of 98, that's most of the people who had that thing measured. And so it lets you get some sense of how common this relationship was, because different things might be found in different people. The thing that was really cool here was we did this over 2 different time periods that were thought to be clinically significant. And we actually find different causal models of these time periods. And the thing that the doctors were really interested in was the variable that I assume 0 people recognize, TW%. It's a proxy for brain swelling. And so what it's saying here is that actually in the initial time period, brain swelling seemed to depend on brain temperature. And then later on, it seemed to depend more on blood flow in the brain, oxygenation in the brain, as well as brain temperature. What's interesting about this is if the causes change over time, the interventions might also need to change over time. And most of the causal inference methods assume that the relationships are static over time, and so you would never observe these. Limitation here is we partition the data using time periods that clinicians thought were significant, which we have no idea if those are the right time periods. It's also possible that that transition or time period might be different for different patients. So we've also had other work I won't talk about here on non-stationarity and change point detection in time series. But it was super exciting. We found some causal models. We wanted to dig more into this. One of the interesting places we went after is looking at consciousness. And so this is, again, a signal that doctors use a lot for making decisions about patients, for understanding prognosis. But it's really time-consuming for them to assess it, and our understanding of consciousness is quite poor. And so my collaborators have had a lot of papers on looking at the role of EEG for assessing consciousness, showing consciousness relates to outcomes. Different factors are associated with impaired consciousness. But the data we have on consciousness comes from instruments like this. And so basically once a day during the morning rounds, someone administers a battery of tests, and they're testing, can you follow my finger with your eyes? Do you respond if I clap behind your head? All these sorts of things. The challenge is you have 1 measurement a day. We have hundreds of thousands of measurements of other variables. And also 2 people can do this and come to a different assessment because it's subjective, right? You have to decide, is this a 5 on the scale or is this a 4? This is another part of it. It's a very crude assessment. And it's time consuming to do it, right? And so that's why you have it once a day. Very hard to assess prognosis or understand factors that are related to consciousness when you have these very irregular and sparse time series. And so what we've been working on is what if we had an automated way of assessing consciousness? And so essentially we have all these other physiologic measurements that are happening every 5 seconds. Are some of them related to consciousness? And so what we've been looking at is using a similar idea as for imputation of missing data. A lot of things are related with time lags, and our hypothesis was that the time lags might be different depending on patients' state of consciousness. And so I won't get into detail on the mathematical machinery. You can ask questions, or for the computer scientists, we can talk about it offline. The idea is also if your consciousness is changing over time, the time lags between the variables are also going to change over time. So we developed new methods for finding lagged correlations and how and when the lags change over time, and are using that to see if there's a signal that relates to levels of consciousness. So the data here was more patients in the neuro ICU. We had a few hundred assessments of consciousness. Again, it's once a day during morning rounds, and it depends on how long the patient's in the ICU and alive. And so you have a different amount of data for different patients, and there's nothing you can do about that, right? You have between 1 and 18 measurements per patient. We focused on the scale gives you a value between 1 and 5 or 0 and 5. We just focused here on impaired and intact consciousness, so at the upper and lower end of the scale for the moment, and not the intermediate parts, partially because of the questions about, can you reliably distinguish between a 3 and a 4? People might use different values on the scale. We're sure that 4 and 5 and 0 and 1 are definitely different. But in between it gets a little bit challenging. Okay, it was moderately successful. Okay, so here's what we found. So this is showing you pairs of a number of different variables we measure in the neuro ICU. And then the time lag of the correlations between those variables for patients with low, which is impaired consciousness, and high, which is intact consciousness. So patients who are alert and able to respond to commands and things like that, versus the comatose patients. And so what we found was in basically every case, patients with intact consciousness had a much lower delay in the lag between these variables, which sort of makes physiologic sense that if things are going well, there's lots of feedback loops in the body, many things are related, and signals would be transmitted in a timely way, versus if things are impaired, then maybe something is going awry along the line, and then you would have a delay in these correlations. Or maybe things would become uncorrelated that are normally correlated, right? That happens also. So it's really cool that these things were also related to a lot of the causal relationships we found. There were a lot of relationships involving brain temperature, oxygenation, swelling, that sort of thing, and it was a totally different method. So it's exciting that the same things seem to be important, and now they're related to consciousness. Oh, this is showing basically the same thing, just showing you p-values and stuff for if you're into that. So it was exciting. I take it you know where this is going. So for me, this was like 5 years of effort. We found all these things that relate to stuff that's happening with the patients. It's clinically meaningful. This is awesome. But I showed you a subset of relationships that involve the brain for a reason, because this is what the whole causal model looks like. And to me, again, after 5 years of effort, this was a thing of beauty. We actually found causes. We believe that they're causes. This was amazing. And then my collaborator, Jan, the neurointensivist, said it's an unholy mess. And so that was sad, but I understand where he's coming from. If I spend 3 hours with him and talk him through all the relationships, then he gets it. If I come back a week later, then I have to start over and we talk through the relationships again and say, he wants to know, things that he knows that aren't here. Why aren't they here? What does this mean? What does that mean? If I change this node, then what happens? Which is not an approach that scales well, right? So I got concerned that now I've been devoting about 10 years of my life to finding causes. Can people actually use these causes, right? It seems worrisome that at least they're not intuitively beautiful to other people. So that's what I've been doing for the last year or so, is understanding, does this actually help people make decisions? And so like Jan, if he goes into the ICU, his interventions aren't on the variable that we have here, heart rate or brain temperature. He can give him medication that might affect heart rate, but it's not the same as directly controlling heart rate as a knob, right? Which is what the figures here tell you. They tell you, if you could intervene on brain swelling or brain oxygenation, here's what would happen and these other variables would be affected. But those aren't the options that we have. And so it's a huge cognitive load to map what's in the graph to what are the actual options and how do these relate? And so it seemed like a much broader problem also, right? We have that in daily life. If we look at what foods or factors affect glucose, you're again not deciding if you're at a breakfast buffet or after this at the lunch buffet, how many carbohydrates should I have? You're deciding, should I have a salad or a sandwich? Should I get oatmeal or fruit or pancakes or whatever? And that's a much harder problem, and nothing in the figure tells you, how do you map that to the specific choices you have? And it's true for, I like to run. So what time should I run? Not just should I run or not. How do you invest for retirement? So the second part of the talk is how do we go from learning about causes or getting some knowledge to actually taking action? The big gap in computer science has been that we evaluate our methods based on accuracy. You can choose your favorite number, but it's basically, do we find more of the causes? Does my algorithm find more of the causes than this other algorithm, right? If I find more of the causes, my algorithm is better. Do I find false causes that shouldn't be there? Okay, that's not so good. Do I find the causes faster with less memory? All that kind of fun stuff. Can I do it with less data? But all that's based on things that are relevant to a machine, not things that are relevant to a person, right? This is all the different options, precision, recall, all of that. But there's nothing that prioritizes, do I find stronger causes or weaker causes, right? Maybe my algorithm finds fewer causes than another one, but actually I find the ones that are stronger versus another algorithm finds a bunch of extremely weak causes that aren't so useful to clinicians. Maybe we care more about causes that are earlier versus other ones because we want to intervene early. Maybe we can't intervene on everything, and so it's useful to know, for example, family history is a risk factor for type 2 diabetes. But if you're a patient, that's something that you can intervene on. So is it super useful for you to know that? Maybe not, right? And we don't really have a sense of what does it mean for a cause to be useful, right? We have no idea. If I want to create a new evaluation for causal inference methods, what should my inference methods prioritize, right? What would be a good causal model versus a bad causal model? We know that Jan thinks my model is an unholy mess, but what would be a good model for Jan, right? That's still an open question. And in psychology, there's been a huge amount of work on how people learn about causal relationships, how people use causes to make interventions. It's been very positive, showing that people actually are very good at finding causes. Often we're too good and we find causal relationships when there shouldn't be. For example, like in the case of the flu shot and the flu. And so we're sort of primed to see causality, but we can learn from very few instances. The problem is all these cases these are sort of representative. These aren't especially chosen for this. They're mind-reading aliens or blicket detectors. I have a box and you put blocks on it. Which blocks are blickets because they make something happen. It's also kind of a tongue twister. You have one with drugs and microorganisms, but it's made-up drugs and made-up microorganisms and very abstract. It's not how do you link what you know about heart rate or diabetes or glucose to this new model that I'm giving you that tells you factors that affect your glucose for a person with diabetes. And so I became worried that there's a gap here between showing people can understand causality in these very constrained settings, and then my collaborator and other people who see the causal model and can't use it at all in cases that they're actually really familiar with, where I thought, hey, this problem, you should be able to use this better than abstract case. So the question we've been working on is, can causal information aid decision-making in familiar cases? And so we've been doing a lot of studies on mechanical Turk, on cases, for example, like managing weight. And there the idea is if we show you a decision-making question where there's one best answer, we show you the question by itself, and then we show it to you with a causal model. Does the causal model help people make decisions? So this is one of our simple questions. So this is showing there's a freshman in college. She has some priorities. She heard about the freshman 15. She wants to avoid gaining weight, but she also wants to have fun, make friends, leave time for homework and studying. And then you get a simple causal model that shows factors that help you maintain a healthy weight. And then the options are she can go for a walk, she can maintain a healthy diet, she can ignore her friends, or watch less TV. Right? So it's a fairly simple question, but it's richer than the mind-reading aliens. Right? It relates to things you already know. The good news is people are very good at answering questions about maintaining weight. So we have 89% accuracy if we just give people the question. The bad news is accuracy goes down quite significantly once we give people a causal model. And so again, after 10 years of my life trying to develop methods and arguing and writing lots of books that causes are great, we should spend all of our time finding causal relationships. Then we give people causal relationships and they do vastly worse. And so that was concerning that, especially went from 89 to 80%. We also showed people the same causal relationships in text form. Text is in the middle. Text was slightly better than a diagram, but wasn't better. And it was still significantly worse than no information. So it didn't seem to be the format of the model, because you could say, maybe if you do visualization, there are better ways to present information. Here, it didn't really seem to matter how it was presented. It was detrimental in all cases. So this was worrying. Looked at a number of explanations. So, the first thing, maybe people are rushing, right? It's a mechanical Turk. Maybe people are just speeding through the task. They're not spending enough time on it. And actually, people spent longer with the causal diagrams versus the text. And so it seems like they are looking at it and trying to make sense of it somehow. And then we thought, okay, but maybe the people who get it wrong are not spending enough time on it, right? Maybe if they just spent more time with the diagram they'll see the light and make use of it. Actually, people who got it wrong did worse, spent a little bit more time compared to people who got it right. And we also asked people things like, did the diagram inform your answer? Did you find it helpful? And there was no difference in whether people got it right if they thought it was helpful or not. So people also weren't very good judges of whether it was useful. I know, that was the face I made. It's depressing. And so, but the question is, maybe all the psychology studies wouldn't predict this. The psychology studies would say people are really good at using causal information. They can learn causes. They can intervene based on them. But again, they're based on constrained settings that aren't related to prior knowledge. And so we thought maybe it's actually because people have prior knowledge that they're doing worse. And so again, it's like going back to Jan, who has a huge amount of knowledge about stroke and what's happening in the neuro-ICU. And maybe it's difficult specifically because he has knowledge, and he's trying to mix what we show him with what he already knows. So now we looked at another case where some people have prior knowledge and some people don't. So this was a question about managing type 2 diabetes. And so if you don't have type 2 diabetes, you probably haven't spent a huge amount of time thinking about how to manage type 2 diabetes. If you do have type 2 diabetes, you've more or less successfully spent some amount of time thinking about your type 2 diabetes. Maybe you don't do what you need to do to manage it, but you have some experience in the domain. We also made the model simpler. Maybe the other one had too many nodes. We simplified down to 3 nodes. Maybe that'll solve the problem. So here, all you have to realize to answer the question is 2 causes are better than 1. That if you have limit carbohydrates and exercise, then that'll be better for your glucose versus if you just do one of those things. So it's a pretty simple problem. We had high hopes for this one. So there was some positive news in that people who didn't have experience, so people without diabetes answering the question, did better, and they did a lot better. Went up from 71 to 87% accuracy. That was really good. So if people didn't have experience, then they were able to actually use the information. But also, if you don't have experience, it makes it more like the abstract questions in the psychology studies, right? If you don't have type 2 diabetes, it could be a problem about anything. You use the model, and you can answer the question. People with type 2 diabetes had lower accuracy overall on the question, and much lower accuracy with the causal diagrams. So that was, again, sort of alarming and concerning. We thought, like, what is going wrong here, right? Its causes are just, making everything just so much worse. So one hypothesis is, okay, maybe was that a question?
Yeah.
Yeah.
Can I ask a question?
Yeah, of course.
Do you think one hypothesis or reason could be that people with type 2 diabetes have experience about their own behavior and also others, and that influences what is sort of a guaranteed causal model versus what actually happens? Like, I work with people with diabetes. I don't have diabetes, but I know people who would say, I do not want the pastry in front of me because it does not matter what the physician tells me. I will eat it as long as it's in front of me. And I will just say, just this time it's okay.
Yeah, so I won't talk about it here, but in other work, we've tried to separate out experience in a domain, proficiency in a domain, which is not the same as experience, and then people's belief in the domain, and it seemed to be experience that was the problem. Experience / people's perceived proficiency, which are also strongly correlated, and which are totally uncorrelated with what they actually know. And that's like, I think in the diabetes case, it was not correlated, and then for personal finance, it was negatively correlated, or the reverse. But essentially, people are very bad at understanding what they know, and it's specifically when people think they know more that they do worse with the causal information. Yeah. But we thought, diabetes is complex. If you know something, maybe you look at this oversimplified thing and you're saying, hey, it doesn't include all the stuff that I know should be there. And so we thought, maybe if we do this with a more complicated graph, then that's closer to the truth, it'll go better. That was very quickly shot down, very much not the case. More causes were not better. But you could see, why we would think that, right? That maybe it's oversimplification, and it's more cognitive burden trying to map it to what you know if it's oversimplified. If you already have a rich causal model, maybe this is closer to your causal model. Definitely not the case, but it was a good thing to try. And so accuracy went just so much worse, right? 63%. And so again, why is this going so badly? And so then we thought, what's going differently in people who think they know stuff versus people for whom it's a novel domain? And then we looked at confidence. And so maybe you see new information and you start rethinking what you already know, right? People were really good with no information in the weight management question. They had 89% accuracy. So it's not that people, don't already know something. They're they have a pretty good idea of what needs to be done, and maybe this is making them rethink that. So we reran everything, and now just added a question saying, how confident are you in your answer to the previous question? And so the experience group are people answering questions about managing body weight. So we've done other studies showing most people think they know a lot about maintaining weight. Whether or not they can do it successfully is a different matter, but people believe this is a domain they know stuff about. And so here, we actually see exactly that. With no information, 83% of people are very confident in their answers. With the causal model, that goes down to 70%. And so it does seem to be crushing people's confidence. And also, interestingly, of the people who were very confident, originally, most of them get it right. So 92% of people who are very confident get it right. The confidence is not misplaced. But with the causal model, even among the people who are very confident, now accuracy is also lower, which is also sad. The sort of interesting thing was we see exactly the reverse in people making decisions in a domain where they don't have experience. So this is people without diabetes answering the question about diabetes management. Initially, most people do not think they know anything about diabetes management. So 42% of people are very confident that in their answer to the question. Of those people, their accuracy is pretty good, right, 87%. But with the causal diagram, many more people are confident in their answer. It goes from 42 to 69%. And now 94% of those responses are correct, which is much larger than the other one. And so again, the diagram is doing different things in people depending on whether they have experience in the domain or not, which was really interesting and also not something that we've thought about in terms of causal inference, right? We infer one model and then just assume it's good for everyone. But actually, the information that's useful is different for different people, and it's going to have different effects with different people. So I'll update my original slide, which actually requires causality, but causality alone isn't quite sufficient, right? And so a few things looking forward. One is we need much better evaluations of machine learning algorithms that aren't just about accuracy, but are about utility. So there's been a lot of work on machine learning and AI about explainable AI, but it's been mostly explainable to a machine learning person. So what are the features the model is using? It's not can you understand it, it's can you actually use this to make decisions in the domain of interest, right? And nothing in explainable AI is going to tell me, is this a model that's actually useful for a clinician or for a patient with diabetes to make decisions about managing their diabetes? And so we need new methods for evaluating the utility of models, right? It could be, does it help you better achieve your goals? Does it help you speed up decision making? That might be important in clinical scenarios, right? And that's not at all captured in current evaluations. And it's something we need to optimize for, not at the end, but as part of development, right? It changes what the methods are going to look like if we're optimizing based on utility versus on accuracy. Second is clearly we need personalization. We show the same model to people with and without experience, and in one group it completely decimated their confidence. The other people felt much more confident with the diagram, right? And so we need to figure out which information is better for different groups and personalized to what people already know. So an interesting sideline is also trying to elicit what people already believe and then build the model in the context of that, which we haven't done here. This is, we learn stuff from data and then show it to you. But we haven't looked at what happens if what you believe conflicts with the model, right, which might also change how you use the model, and all the stuff over there. It also creates some concerns for shared decision making. So there's a lot of work, especially in diabetes, about how shared decision making should be a goal. But if you and a doctor have different beliefs and then we present new information at the time of decision, it's going to be interpreted completely differently by everyone, and it's not going to lead to an effective decision. And lastly, we need to capture and model the decisions so it forms a feedback loop back into the causal inference, right? We should be capturing what interventions do people choose, what do people ultimately decide, and then use that as part of the inference process in the end. So I'll end there. This was collaboration with people at Columbia, Lehigh, Stevens. It's been generously funded in the US, and also I'm hiring postdocs both in computer science and cognitive science. So I'll stop there and I'm happy to take questions.